criterion. Let's first notice that geometric multiplicity. Okay, geometric multiplicity is at most the algebraic multiplicity. So if mu is the characteristic value or the eigenvalue of a given linear transformation or a matrix, then that mu is algebraic multiplicity. It is always bounded below by the geometric multiplicity, which is the dimension of the eigenspace. So suppose V is a finite dimensional vector space, then the geometric multiplicity of an eigenvalue of T is less than or equal to algebraic multiplicity. Okay, and we will see what happens if it is equal. But in general, the geometric multiplicity is bounded above by algebraic multiplicity. So let us prove that. Suppose that the algebraic multiplicity is k. Okay, that means x minus mu. X, the largest power of x minus mu, which divides the characteristic polynomial, is k. Okay, yeah. And suppose the geometric multiplicity is L. So L is the dimension of the eigenspace corresponding to eigenvalue mu. Okay, so I have these two numbers associated with this eigenvalue. So the eigenspace is V mu and its dimension is the geometric multiplicity L. That means V mu has a basis consisting of L eigenvectors. I can find L eigenvectors inside the eigenspace which form a basis of V mu. Yeah, but V mu is actually a subspace of V, and I have a basis of this subspace V1 up to VL, and we have proved that any set of linearly independent vectors can be enlarged to a basis of V. I can enlarge this to a basis of V. Okay, so we can extend V basis of the eigenspace to an ordered basis of V, and so by adding n minus L vectors, I can form a basis of the whole space. Yeah, the first L of them are eigenvectors corresponding to eigenvalue mu. The rest I don't know. They are some part of the basis of the big vector space V. But I have a basis of the vector space V, and then with respect to this basis, I can find the matrix and then calculate the characteristic polynomial. The characteristic polynomial of the linear transformation can be computed by fixing any basis. Yeah, can be computed by fixing any basis. So I can fix this basis B, whose first L vectors are eigenvectors. Okay, now I find the linear transformation, which is I find the matrix of the linear transformation with respect to this basis. So how to find the matrix? Well, operate T on the basis vectors. So TV1 under the action of T goes to lambda 1. I mean mu times V1. V2 under the action of T goes to mu times V2, etc. So up to VL, it will be mu times VL. Okay, yeah. So therefore, the coordinate vector of TV1, TV2, TVL will be very simple. It is for the coordinate vector of TV1 is lambda 1 on lambda 1 0, mu 0 0, etc. Coordinate vector of TV2 is 0 mu 0 0, etc. etc. So the first L column vectors of the matrix, yeah, they are very simple. They look like mu 0 0, 0 mu 0, etc. And the Lth one will be 0 up to mu. So I have this L by L matrix, which is a scalar matrix. The diagonal entries are the eigenvalue mu, other entries are 0. So this is this matrix. Yeah, and then once I start operating T on the remaining vectors, TVL plus 1, TVN, then I don't know what they are. Yeah, so they will be some their coordinate vectors with respect to V will be some general column vectors. Yeah, so I get this kind of matrix, yeah, of the linear transformation. Yeah, this is the 0 matrix, and this part are some n minus L column vectors in Fn. So this is the matrix, and now we find its characteristic polynomial. How to find the characteristic polynomial matrix? It is just look at xi minus that matrix and find the determinant. Yeah, so if you find the determinant, let's call this matrix as A, then determinant of xi minus a will involve x minus mu, x minus mu, x minus mu, etc. There will be other terms, okay, but these are all zeros here. These are all zeros here. So determinant of this will have a factor x minus mu to the power L. Okay, so x minus mu to the power L will be a factor of the characteristic polynomial, right? And therefore the algebraic multiplicity of mu is bigger than or equal to L, because Lth power of x minus mu divides the characteristic polynomial. The bigger power may divide. Yeah. So and L was the geometric multiplicity. So I have proved that the algebraic multiplicity of an eigenvalue is at least the geometric multiplicity. Okay, it will be nice if it is equal, and let's see what happens. Yeah. So this is the criterion for diagonalizability, that if the eigenspace of every eigenvalue has same dimension as the algebraic multiplicity of that eigenvalue, then and only then the linear transformation or the matrix is diagonalizable. So I can state it for linear operator, and a theorem about linear operator implies same theorem about matrices, because given a matrix A, then it gives rise to a linear operator on the vector space. Yeah. So take a linear operator on a n-dimensional vector space over the field. Then T is diagonalizable. That means there is a basis of eigenvectors of V if and only if the sum of the dimensions of the eigenspaces is equal to dimension of V. Yeah. So eigenspaces, they fill up the whole space. If I add the vectors in, if I take the linear span of basis of each eigenspace, yeah, I will get the entire vector space. Okay. Now eigenspaces intersect only in the zero vector. This I have proved before. Any two eigenspaces correspond to distinct eigenvalues. They intersect in zero vector alone. So the dimension, the sum of the dimensions of various eigenspaces is actually the dimension of the sum of the eigenspaces. So when I add up the eigenspaces, it becomes the whole space, which means that there is a basis of eigenvectors if T is diagonalizable. This fact is equivalent to saying that there exists a basis of eigenvectors. Okay. Now this is with respect to any field of scalars. I am not distinguishing between real field or complex field. So this is the general criterion, that eigenspaces are big enough so that they fill up the whole space. Yeah. Then and only then the linear transformation is diagonalizable. Now take the special case when the field of scalars is complex field. Okay. Then we can say a better statement that a linear transformation or a matrix is diagonalizable if and only if the algebraic and geometric multiplicities are equal for every eigenvalue. So this is a testable numerical criterion. Suppose I'm dealing with a matrix. Yeah, dealing with a matrix. First I construct its characteristic polynomial, find out all the roots. We know that the roots are there. If the field of scalars is complex field, then by fundamental theorem of algebra, every polynomial with complex coefficients of degree n has n roots counted with multiplicity, and so if I look at each and every eigenvalue, in general there are n eigenvalues in the field of complex numbers, and for each eigenvalue I find eigenspace. Eigenspace is what is the eigenspace? It is the set of all vectors so that t minus lambda I v equal to 0. So I find the null space of the given linear transformation or the matrix. Computing null space is solving a system of linear equations, homogeneous system of linear equations. So for every eigenvalue, I find the eigenspace, and the dimension of that eigenspace is the geometric multiplicity, and this criterion says that over the field of complex numbers, a matrix or a linear transformation is diagonalizable if and only if the algebraic multiplicity is exactly equal to geometric multiplicity. There's no gap. Geometric multiplicity by earlier result is less equal to the algebraic multiplicity, but diagonalizability is characterized by equality of algebraic and geometric multiplicities. Yeah, so let us prove that. Okay, this is a sketch of a proof. I have explained most of the principles to which will go into the proof. So suppose look at part A. I want to prove that if T is diagonalizable, then the dimensions of the eigenspaces will add up to the dimension of V. So suppose T is diagonalizable. What is the definition? If it is diagonalizable, there is a basis of eigenvectors. Yeah, there is a basis of eigenvectors. So, but these eigenvectors are inside these eigenspaces. Yeah, they are inside these eigenspaces. So lambda 1, lambda k be the distinct eigenvalues of this linear transformation. So I have k distinct eigenspaces. Any two of them intersect only in the zero vector. Yeah. So if whenever this property is there among subspaces, that any two subspaces will intersect only the zero vector, then the dimension of their sum is the sum of the dimensions of the vector spaces. So I take a basis of each of the eigenspaces V lambda I, and I look, since the intersection is 0, then B1 union B2 is a linearly independent set of vectors, because there is the only zero vector is common between these two vector spaces. So if I take the basis of V lambda and basis of V mu, then their union is linearly independent, and so therefore so that dimension of V lambda 1, V lambda plus dimension of V mu is the dimension of the sum. Okay, and so that shows by induction, we keep doing this. It says that if I line up basis of each eigenspace and take the union, it is also linearly independent. But I have a basis of eigenvectors. So this basis of eigenvectors is consisting of one vector from each of the eigenspaces, or several vectors from each of these eigenspaces. Number of eigenvalues can be smaller than number of the dimension of the eigenspace. Just take identity matrix. Identity matrix has only one eigenvalue. Because it is a diagonal matrix, it has only one eigenvalue, lambda equal to 1. But the entire space consists of eigenvectors. The non-zero vectors in the entire space are all eigenvectors. So the number of eigenvalues could be very small, but the linear operator or the matrix can still have a basis of eigenvectors. Yeah. So since the T is diagonalizable, it has a basis of eigenvectors, and so these n eigenvectors are selected from these. We can select these from these bases of individual eigenspaces and make a basis. So therefore, we have a basis of eigenvectors of T, and the dimension of V is the sum of the dimensions. Yeah, because V lambda and V mu intersect only in the zero vector. Okay. The converse assumption ensures that V has a basis consisting of eigenvectors of T, and therefore T is diagonalizable. Okay. This assumption says that I can find a basis of eigenvectors. Some of them will be in V lambda 1, some will be in V lambda 2, etc., etc. And so T will have a basis of eigenvectors, so T will be diagonalizable. Right? Now assume f equal to c. Then the characteristic polynomial splits into linear factors. Okay, every complex polynomial of positive degree splits as a product of linear factors, and so the number of I pick the distinct eigenvalues. Number of eigenvalues can be smaller than the order of the matrix, like the identity matrix has only one eigenvalue. So pick the distinct eigenvalues, and then the characteristic polynomial factors as x minus lambda I to the power mi. So these mi's are the algebraic multiplicities. Okay, these are the algebraic multiplicities. Yeah. So since the sum of the algebraic multiplicities is n, yeah, that's what this says. Degree of the polynomial is n, and so sum of the algebraic multiplicities is equal to dimension of the vector space. So if T is diagonalizable, then there is a basis of eigenvectors, and so once there is a basis of eigenvectors, the dimension of the eigenspaces have to be equal to mi. Yeah, because dimension of eigenspaces are smaller or equal to the algebraic multiplicity. Yeah. So if So if I take dimension of V lambda I, this is smaller or equal to Mi. Okay, so Mi minus dimension of V lambda I, okay, sum, right? This is equal to sum of Mi minus sum of dimension of V lambda I. Okay, so if all the geometric multiplicities are equal to algebraic multiplicity, the left hand side is 0, so the right hand side is 0, and therefore n is equal to sum of the dimension of Vi. So by part 1, T is diagonalizable. Yeah, T is diagonalizable. So conversely, if algebraic and geometric multiplicities are equal for each eigenvalue, then it follows that the sum of dimension of V lambda is T, so T is diagonalizable. Okay. Yeah. So if my field of scalars is not complex numbers, then diagonalizability criterion says that this dimension of the eigenspaces should add up to dimension of the whole space. If my field of scalars is the field of complex numbers, then I should say that the algebraic multiplicities and geometric multiplicity of each and every eigenvalues are one and the same. Then and only then the linear transformation of the matrix is diagonalizable. Okay, let's look at some examples. Any questions so far? Okay, so let's look at this example of 3 by 3 matrix, and we want to understand whether it is diagonalizable or not, what are the dimension of eigenspaces, how to find eigenvalues. So take this 3 by 3 matrix. First task is to calculate the characteristic polynomial, which is determinant of xi minus a, and that is equal to x minus 3 square x minus 6. Okay, I'll leave this calculation to you. So we have factorized. We may not be able to factorize all the time. Yeah, if my matrix, if I consider my matrix over the field of complex numbers, then of course there will be the characteristic polynomial will split as a product of linear factors. But if my linear transformation is over a real vector space, then the characteristic polynomial may have some complex roots, like the rotation matrix has complex roots. There are no real roots for non-trivial theta, right? So try to find the eigenvalues in the field of scalars. In this case, it is easy. There are two eigenvalues, 3 and 6. The algebraic multiplicity of 3 is 2, and algebraic multiplicity of 6 is 1. Yeah. So if I have an eigenvalue, there is an eigenspace, and eigenspace consists of all vectors so that AV equal to lambda V or TV equal to lambda V. So eigenspace is at least one dimensional. Whenever eigenspace exists, it is at least one dimensional. So if some root has algebraic multiplicity 1, immediately it says that the geometric and algebraic multiplicity of that eigenvalue are equal. So there is eigenspace corresponding to this eigenvalue 6, and there is eigenspace corresponding to the eigenvalue 3. To check whether the matrix is diagonalizable, I have to see that the dimension of E3 is 2 and dimension of E6 is 1, because 1 is the algebraic multiplicity. But the dimension of E6, we know that it is at least 1, and it can't exceed the algebraic multiplicity, which is 1, and therefore dimension of E6 is precisely equal to 1, which is the algebraic multiplicity of the eigenvalue 6. So I have to just look at the eigenspace corresponding to the eigenvalue 3. Yeah. So eigenvalue 3 has algebraic multiplicity 2, because that is the multiplicity as a root of the characteristic polynomial, and algebraic multiplicity of 6 is 1. Now let's find the eigenspaces V3 and V6. Okay. To find the eigenspace V3, I have to solve the equation a minus 3i x equal to 0. This is a homogeneous system of linear equations. So using Gauss elimination, I can find all the solutions here. But pause a little bit. A minus 3i is this matrix, and this matrix has rank 1, because look at this row. This is 0 row, and this row is same. So the rank of this A minus 3i is equal to 1, and therefore nullity of A minus 3i is equal to number of columns minus the rank, which is equal to 2. So, but nullity of A minus 3i, the null space of A minus 3i is precisely the eigenspace corresponding to eigenvalue 3, and therefore this has dimension 2, and 2 is the algebraic multiplicity. So we are in good shape. The algebraic multiplicity and geometric multiplicity of the eigenvalue is precisely 2. Yeah. So nullity is 2, so geometric multiplicity is 2, and so we are done. So there are 2 eigenvalues. Each one checks that the geometric and algebraic multiplicities are equal, and therefore this matrix is a diagonalizable matrix. How to find a basis of eigenvectors? Well, I have this E3 and I have E6. This is dimension 2, and this is one dimensional. This is a 3 by 3 matrix, so it is, I can think of this as a matrix over R3 or a matrix over C3. It is same because both the eigenvalues are real. So if I think of the linear transformation acting on R3, then it has 2 eigenspaces. One is 2-dimensional, another is 1-dimensional. Inside this 2-dimensional eigenspace, I can find a basis of eigenvectors. There are 2 eigenvectors inside E3, which are linearly independent, and I find a eigenvector in E6. Yeah. So then line them up. V1, V2, these are eigenvectors inside E3, which are linearly independent, and pick a eigenvector V3 inside E6, and then we know that E3 intersection E6 is 0 vector, and so if I put together these 2 bases, I have a basis of R3. So I will find a basis of eigenvectors of the given matrix. Okay, that's the general algorithm. All right. So this, I did this calculation before. Null space of A minus 3i is the eigenspace V3, and these are the 2 basis elements, and then we can find for the other eigenvector also. Okay. Yeah. So let's look at the other one. Lambda equal to 6. As I said, this is 1-dimensional eigenspace. The algebraic multiplicity is also 1. And so the rank of A minus 6i, you can check, it is 2. Dimension of the eigenspace is 1. And so 0, 1, 1 is an eigenvector. And that's a basis of V6 because V6 is 1-dimensional. And so I just put together these first 2 eigenvectors are corresponding to eigenvalue 3. And then this last eigenvector is corresponding to eigenvalue 6. So these are 3, 3, and 6. So therefore, P inverse AP will be a diagonal matrix, and the diagonal entries are according to eigenvectors in the matrix P. First 2 eigenvectors are corresponding to eigenvalue 3. The last eigenvector is corresponding to eigenvalue 6, and therefore this is the diagonalization. So I have diagonalized the matrix. 3, 3, 6 diagonal matrix is similar to the given matrix A, and you can see that the characteristic polynomial here is lambda minus 3 square times lambda minus 6. Okay, so the basis of eigenvectors is going into the matrix P as column vectors. So I line up all the column vectors which are consisting of eigenvectors of A, and then it follows that P inverse AP is this diagonal matrix. So keep in mind the order in which the eigenvalues are placed on the diagonal, that is same as the order in which we line up the eigenvectors inside P. Okay. Yeah. Let's look at this matrix. Very simple looking matrix. 1, 1, 0, 1. 2 by 2 matrix. They calculate the characteristic polynomial. It is x minus 1 square. There is only one eigenvalue. Yeah. There is only one eigenvalue of this this matrix. And so if this matrix was diagonalizable, then the eigenspace corresponding to eigenvalue 1 should be 2-dimensional, right? Because the algebraic multiplicity is 2. So geometric multiplicity should also be 2 if this A was diagonalizable. Let's calculate the eigenspace corresponding to lambda equal to 1. Yeah. So in order to do that, we have to look at the system of homogeneous linear equations A minus lambda I x equal to 0. So in this case, you can solve that and look at A minus I, because lambda is equal to 1. So I have A minus I A minus identity matrix is this matrix. Okay, so this matrix has rank 1. Rank of A minus I is 1. So nullity is also 1 because the rank and nullity they add up to number of columns. So the null space of A minus lambda I, which is the eigenspace of lambda, is one dimensional. So eigenspace of the eigenvalue lambda equal to 1 is one dimensional. Yeah, so it is smaller. The geometric multiplicity is 1, algebraic multiplicity is 2. So you cannot have a basis of eigenvectors because eigenvectors have to live inside the eigenspace, and eigenspace is too small. It is one dimensional. The whole space is two dimensional. So I cannot have basis of eigenvectors. There is only one eigenvalue. So this matrix is not a diagonalizable matrix. Yeah, very simple looking matrix, but it is not a diagonalizable matrix. Okay, yeah, because geometric multiplicity is 1, algebraic multiplicity is 2 of the only eigenvalue.